Welcome back to The Explainer. Today, we're embarking on a seriously staggering cosmic journey. We're going to look way past those dry, rocky cinders that usually dominate exoplanet discoveries, and instead, we're diving deep into the quest to find out if the cosmos is just teeming with hidden aquatic alien life. If you're fascinated by the hidden mechanics of our universe, well, you are in the exact right place. So let's get into it.
You know, when we look at a globe, it's really easy to be fooled by the illusion that Earth is the ultimate water world. I mean, 71% of our surface is covered in it, right? But honestly, our oceans are essentially just a thin layer of surface condensation. It's basically a wet film compared to the sheer volume of water that exists on other celestial bodies out there in the dark.
Okay, let's dive into this. Pun definitely intended. To really grasp what we're looking for, we need to define what an ocean world actually is. We're talking about stable, globe-girdling bodies of liquid water, or, occasionally other fluids, that completely submerge a planetary surface. These true ocean worlds boast oceans that can be tens or even hundreds of kilometers deep, absolutely dwarfing the total water volume we have here on Earth.
Section 1. Oceans in our solar system, the local laboratory.
So, we have this incredible paradox of fire and ice. Think about Earth for a second. Despite all its surface water, it's fundamentally a rocky body. But when we look at ocean moons, it's a totally different story. These moons have freezing, incredibly thick outer crusts of solid ice, but beneath that armor, they're hiding deep, globally encompassing liquid oceans.
And the targets we've identified right here in our own stellar neighborhood are just mind-blowing. We've got Jupiter's moons, Europa, Ganymede, and Callisto. Over at Saturn, there's Titan, which has these bizarre oceans of ammonia and hydrocarbons, and of course, Enceladus. Actually, our fascination with Enceladus went through the roof back in 2005 when the Cassini spacecraft spectacularly spotted active water vapor geysers shooting right out from its icy South Pole. Absolutely wild.
Just think about the sheer scale here for a moment. On Enceladus, the ice crust alone is a massive 21 to 26 kilometers thick. But right beneath it, a global ocean with a depth of 26 to 31 kilometers. That incredibly thick ice layer acts as a sort of cosmic shield, creating a highly protected, potentially habitable aquatic environment underneath.
And then we have Europa. Europa's subsurface ocean is estimated to be a staggering 100 kilometers deep. But here's the kicker. It boasts an Earth-like salinity of about 35 parts per thousand. And crucially, the liquid water is in direct contact with the moon's rocky seafloor. Now, why does that matter? Because that direct contact is an absolute game changer. It allows for vital water-rock chemical reactions, which are the fundamental engines for generating the energy needed to support life.
Section 2. Heat in the freezing deep. How subsurface oceans stay liquid.
So the obvious question is, how do these oceans not just freeze solid? Well, for moons like Europa and Enceladus, the answer is a mechanical marvel called tidal heating. Because these moons have eccentric orbits around massive gas giants, the immense gravitational pull literally stretches and squishes the moon as it orbits. This constant gravitational tug-of-war creates tremendous internal friction, acting like a giant heat engine that melts the ice and sustains these vast liquid oceans for billions of years.
But what about cold exoplanets way outside our solar system? That brings us to basal melting. Deep within a planet's rocky crust, long-lived radioactive isotopes like uranium, thorium, and potassium decay and release geothermal heat. This heat slowly rises and melts the very bottom layer of a massive, kilometers-thick ice sheet. So the thick ice above basically acts like a cosmic cooler, insulating that subglacial ocean below and keeping it perfectly liquid.
Section 3. Exoplanets and Hycean worlds. The deep space frontier.
Now we get into the really mind-bending stuff. Have you ever heard of a Hycean world? It's a mashup of hydrogen and ocean. We're talking about hypothetical hot, water-covered planets blanketed by a thick, dense hydrogen atmosphere. Take the exoplanet TOI 270d, for instance. It's a fascinating target, though to be completely fair, scientists are still debating its true nature. Some data points to a global ocean, while others suggest it might just be a rocky world completely covered in dense, incredibly hot steam.
Let's shift gears and see how this builds our understanding of what's out there. If we travel exactly 100 light-years from Earth into the Draco constellation, we find a truly fascinating super-Earth that is currently turning a lot of heads in the astronomical community. It's called TOI 1452b.
Notice the stark mass difference here.
Earth sits at 1 Earth mass naturally, while TOI 1452b weighs in at 4.82 Earth masses. But here is the crazy part. Despite its massive size, its measured density is surprisingly low. And that low density strongly suggests that a huge fraction of this planet's mass isn't just dense rock and metal, but volatile materials, specifically enormous amounts of water.
The significance of this literally cannot be overstated. Charles Cadius, the lead researcher from the University of Montreal who studied its unique properties, put it perfectly. TOI 1452b is one of the best candidates for an ocean planet that we have found to date. It is absolutely a prime target for future observation to see if it truly is a globe-spanning ocean.
We also see enormous potential in the famous TRAPPIST-1 system. Looking at the data, tidal heating plays a huge role here, too. Planets D and E sit right in a temperate sweet spot, completely avoiding the extreme, sterilizing heat of their inner neighbors. Planet D enjoys moderate tidal heating, keeping surface temperatures at a very comfortable 15 degrees Celsius. That's about 59 degrees Fahrenheit. Meanwhile, Planet E is colder, more like Earth's Antarctic region, but still perfectly viable for sustaining water.
Section 4. The ingredients for life, the habitability equation. Now, as you know, life as we understand it requires 6 ubiquitous chemical building blocks, the CHNOPS elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Finding these specific elements in a state of chemical disequilibrium, meaning they are actively reacting with each other rather than just sitting inert, is the absolute holy grail for scientists studying those subsurface oceans on Europa and Enceladus.
So the really crucial point is how life gets its energy in the total dark. Life under miles of ice obviously cannot use photosynthesis, right? There's no stellar radiation or sunlight down there. Instead, it must rely on chemosynthesis. This means utilizing chemical energy generated from water-rock reactions at the ocean floor. To processes like serpentinization or hydrothermal vents provide the heat and the nutrients necessary for microbes to just thrive in total darkness.
Section 5. Challenges of future exploration. Drilling into the unknown.
The hurdles we face are, frankly, massive. First, we have to somehow penetrate tens of kilometers of rock-solid ice crust. Then, you've got the extreme pressure at the ocean floor. There's also this fascinating and terrifying biological risk called vitrification. That's where tectonic shifts in the ice could force microbes upwards, flash freezing them instantly. And on those massive exoplanetary water worlds we talked about, extreme pressure can actually turn bottom water into high-pressure ice, physically decoupling the ocean from the nutrient-rich rocky core and completely stifling its biological potential. But overcoming these bottlenecks is the next great leap in astrobiology, and we're already gearing up with upcoming missions like NASA's Europa Clipper and the ESA's JUICE probe. Future drilling missions are going to require unimaginable feats of engineering and, exorbitant costs. But beyond the tech, we absolutely must exercise extreme planetary protection. We have to figure out how to pierce the icy armor of these moons and analyze their chemistry without our Earthborne probes contaminating what could be pristine, habitable, and currently living ecosystems. Which brings us to the most profound thought of all. These oceans are out there. They're churning beneath miles of ice, warmed by gravity and radioactive decay, and potentially rich with the chemical building blocks of life. So, when we finally manage to crack the ice of Europa or Enceladus, will we look into those dark hydrothermal depths and find that we are not alone in the universe? Keep that question in mind as we watch this all unfold in the coming decades. Thanks for joining me on this explainer, and keep looking up.